Hello and welcome back to video 2. So this is part 2 from my AP Calculus AB course, review course. We are going to continue taking notes and going over content from Unit 2, which is limits and continuity. It's the review unit. So everything in this series of videos for the Unit 2 review are the important aspects of limits and continuities within that unit. So we're not going over every single nook and cranny, but this is the important review part. Okay, so let's begin. We left off right here with limits as x approaches positive or negative infinity. Uh, the first two limits we have listed here, okay, if we have a limit as x goes to infinity or as x goes to negative infinity, all right, whatever value that equals gives us a horizontal asymptote, okay? It gives us a horizontal asymptote at y equals whatever b value this is, okay? Same thing here at y equals b. So whatever value, numeric value that ends up equaling, okay, that's where we have a horizontal asymptote. So how do we figure out something like that? Well, let's say I have the limit as x approaches infinity of, I don't know, 5x squared all over 2x cubed minus 7. Yep, that would be cubed minus 7. The easiest way to do this is I take the biggest term on the top and I take the biggest term on the bottom. I simplify it, okay? And then I plug in an infinity for x if there are any x's left. So my biggest term at the top, well, there's only one term. It's 5x squared. My biggest term at the bottom is 2x cubed. So I end up with 5x squared over 2x cubed. Now, someone could say, well, Visca, what happens with this negative 7? If I throw an infinity in for this x and I cube it, does it matter if I subtract 7? No. 7 is so infinitely minuscule and small compared to infinity, it really doesn't matter. That's why we only keep the biggest terms, okay? The biggest term in the top and bottom. So I keep this, I have it here, and I reduce it if I can, meaning I can take 2 x's off the top and 2 of these 3 off the bottom. So now I have 5 over 2x, okay? I can't reduce it anymore, so now I plug in infinity. Okay, so I get 5 over 2 times infinity is just infinity, okay? Now, whenever I do this process, there are one of 3 things or outputs I'm going to see. If I have a fraction where the bottom grows faster than the top, it will approach 0. Okay, so my limit would be 0. Therefore, I would have a horizontal asymptote at y equals 0. Okay, well, what happens if the top grows bigger than the bottom? Okay, let's say I have another scenario, I reduce it, and I end up with like x on top and a 5 on the bottom, so it's infinity over 5. We would say the limit is infinity, or there is no limit. It's undefined. Okay, the limit is infinity. Okay, I would go with infinity. That means there is no horizontal asymptote here. No horizontal asymptote. So here are 2 of the 3 scenarios. I can end up with an x in the bottom and not on the top, which means the bottom would have infinity. Okay, and it would grow faster, which means it would approach 0. Here's a second scenario. Okay, I would have an infinity on top and not the bottom. Or I would have a situation where the top grows faster than the bottom, which means the limit would be infinity, okay, which means there's no horizontal asymptote. So what's my third scenario? My third scenario would be the following. If I ended up with no x left, so the biggest term in the top and the biggest term in the bottom both had an x and they canceled. Well, now there's nothing to throw infinity into, which means my asymptote would just be the value I ended up with, okay? If there's no x to plug infinity into, well, then I don't have to plug infinity anywhere. Okay, so those are my three scenarios that I can end up with. All right. The only thing I'm going to say about negative infinity is be careful when you have exponents that are negative. Remember, you need to flip them to make them positive. All right. And if you are applying even or odd exponents, okay, to negative values. Of course, if I have a negative value to an even exponent like 2, if I square a negative number, okay, it's going to turn out positive. Same thing with infinity. If I square negative infinity, it turns positive infinity. But if I cube, if I raise it to an exponent that is odd, if I have a negative value raised to an odd exponent, meaning if I have negative infinity and I square it, I end up with positive infinity. If I have negative infinity, but my exponent is odd, that will remain negative, okay? Same thing with exponents. If I have 5 to the x, okay? If I have 5 to the negative infinity, that would be the same as saying 1 over 5 to the positive infinity. Because remember, I got to flip that, negative exponents to make it positive. So just be careful when you're plugging in negative infinity, because sometimes it's going to mess with the sign of your result. All right? Now, that's for the top half here, which I think is by far the more important of the two. Now, this bottom half, okay, if the top half dealt with horizontal asymptotes, the bottom half here deals with vertical asymptotes. Now, I don't like doing this. I don't teach it this way. I just say whatever makes your function undefined, whatever x value makes it undefined, you're probably going to end up with an asymptote there somewhere. Okay? And let me give you an example of how this works. In fact, we did one here, but it's still a mess. This whole mess right here. Oh, we don't want the crayon. We want the highlighter. We started out with t squared minus 3t plus 2 over t squared minus 4. I factored it into t minus 2 times t minus 1 up top and t minus 2, t plus 2, okay, on the bottom. Now what happened was my t minus 2's canceled. When I cancel something, that creates a hole. But what doesn't cancel is where my asymptote is, meaning what value of t here would make this bottom undefined when t is negative 2. So I would have a vertical asymptote there. Now this is a mess, so I'll give you another example, okay, a clean one on the next slide. But I just wanted to go back to something we had already done and apply our knowledge here. So let's look at here. Let's say I have x, let's do this, to 2x minus 6 over x squared minus 9, okay? What values of x make this undefined? Well, I can tell you right now, positive and negative 3 make this undefined. But we got to be careful. Let's factor and reduce if we can. I can factor out a 2 on top and get an x minus 3. And if I factor the bottom, it's x minus 3 times x plus 3. So we got to be careful with what makes this undefined, because my x minus 3's cancel. Okay? X being positive 3 would have made this undefined. But when it's canceled, that means there's a hole, not an asymptote. All right? There's a hole at positive 3, not an asymptote, because that's no longer in our equation. Okay, it was in our original equation. That made this original one undefined. But this acts just like this does. What I have left is 2 over x plus 3. Okay? So this right here, graph looks just like this, with the exception that there's a hole at 3. How come? Because we really didn't start with this. We started with this, and we got to consider that. Okay? Positive 3 makes this undefined, but it doesn't make this undefined, does it? It doesn't. So that's why there would be a hole there. The graphs look the same, except there's a hole for the graph. Now, what about my vertical asymptote? Whatever makes the function undefined, that is not canceled out, that you can't get rid of, okay? Right now, when x is negative 3, that makes this undefined. That's where I get a vertical asymptote, okay? That's where I get a vertical asymptote. So let me explain this one more time. I look and I say positive and negative 3 make this undefined. Yeah, we said that in the beginning. But at positive 3, there's a hole because it got taken out, okay? Negative 3 is the vertical asymptote because it remained in. So I wanted to show you the difference between something that gets factored and canceled out, gives you a hole, and something that doesn't, gives you the asymptote. Continuity. There is probably at least one question every year on the AP Calculus AB exam that asks if something is continuous and you have to justify your answer. This right here is how you justify continuity. Let me explain what this means, and I'll give you a little bit of an example. I have a function f of x, okay? Let's make it easy. I'm going to write this off to the side here. Let's say f of x equals, I don't know, 2x minus 3, something like that. Now, let's make it x squared. Let's always go to parabolas. Okay? Okay? The limit of my function as x goes to some value c has to equal f of c. What's f of c? F of c is really the y value, okay? If I plug in a coordinate, let's look at my example I have here. Let's pick a number 4, okay? What's f of 4? Well, that's 4 squared, which is 16, really. I'll just write it right here. I think we're grown up enough and smart enough. We know it's 16. This is really a coordinate. When this is your x value, okay, this whole thing equals your y value. This is an x value. It's a when they give you this is the coordinate 4, 16. Okay, 4, 16. Every time. You should train your brain to think that. Okay? So, our f of x equals x squared. If I take the limit of f of x as x approaches 4, that has to equal f of 4. It has to be continuous. It has to, which means my limit as I approach the x value of 4 from the left and from the right side should point to the same y value that I get when my x value is 4. Okay? This output should be the same as this y value. Let me explain that visually with our example right here. Okay? I have coordinates. All right? And I have a parabola. And okay, this is when x approaches 4. Okay? Now, if I have, okay, let's say this point right here, right here. Okay? Now, here's 16. As I approach 4, okay, from the left and right hand side, and I'm going to put a little eraser mark right here for a second. I don't know what's there. I don't know if it's a hole, a point, or whatever. I mean, I do. It's a parabola. But for the sake of taking the limit, as I approach it from the right side, and I approach it from the left side, it equals a y value of 16, okay? So, I can say the limit as x approaches 4 from the left of f of x equals the limit as x approaches 4 from the right of f of x, and that's 16, okay? Equals, okay? They both approach it. This is my limit. This is the answer to this right here, 16. Does it actually equal the point? I hope so. The point right here, that coordinate is actually 4, 16. When I plug in 4, I get an output of 16. f of 4 actually is 16, right? Because f of x is x squared. What happens when I throw my 4 in here? I get 16. So it does equal 16. Okay? So what's the big deal here? Let me explain something to you. If this was a hole here, and let's say I put a point at 17. Okay, let's say this was a piecewise function. Okay? Let's say it said f of x is x squared for everything except when x, okay, x can't equal 4. For everything else, x squared. When x equals 4, or excuse me, boom. You use the number 17 when x equals 4. That's this coordinate dot I just did there, right? The limit is still 16. As I approach 4, it's still 16. But what's f of 4? F of 4 is 17. Okay, this would be 17, so it wouldn't be continuous. Why not? There's a hole here. It's not continuous. The only way is if it equals 16. If the point is where the limit should be. If my point in purple here is where the limit is, look at that. It fills it in perfectly, and it is continuous. If the point is not there, if it's anywhere else, ooh, wow, look at that. Let's get rid of this just so you don't see these coordinates. Okay? If this point is here, obviously it's not continuous. If the point is here, right at 16 is continuous. If it's here, here, wherever, the actual coordinate has to be where the limit is, so I know it's filled in, and I know it's continuous. Let's take a look at an example of continuity when they give you the graph. Okay? Given the graph below, is f of x continuous at x equals 1? What about at x equals 1/2? All right, well, let's do 1 in red. Here's where x is 1. Okay, and this whole line here, everywhere in that line, x is 1. Is it continuous there? It is not. How come it's not continuous? There is a hole right here. Okay, I should be able to go through the number 1 without picking up my pencil or pen. Okay, I cannot. I go up here, hole, I put the point here they give me, and I continue down here. Even if I didn't have another coordinate, okay, even if I didn't have this coordinate here, yep, that's the eraser. If I didn't have this, I would go up, pick up my pencil, put it back down, and continue. That is not continuous. Is x continuous at 1? No. How come there's a hole there? It doesn't ask you for the reason, but I'm giving you the reason. Okay? Now, what about when x is 1/2? Well, Mr. Visca, I don't see 1/2 here. I don't know. Isn't 1/2 between 0 and 1? Okay. 1/2 would be somewhere on that line. Okay. Actually, it looks like it's right around there. Yeah, it's continuous at that point because I can go through that point without picking up my pen or pencil. Okay? Yes. It's continuous there. To me, it's so much easier to see on a graph, a visual picture, if it's continuous or not, if it's a continuous line, continuous curve. Okay? So now that we've kind of discussed what continuity is on a graph, okay, if I can draw it, okay? If I can draw this from this point to this point, if I can draw a continuous function or graph from those 2 points, I just draw without picking up my pen or pencil. Boop. If I have to pick up my pen or pencil, you like how I did that? Boop. If I have to pick up a pen or pencil at any point when I'm drawing between these two, it's not continuous. Okay? A hole. It's a hole. Well, I go like this here. Okay, there's a hole there. Then I keep on going like this there. Boom. Right here's a hole. That's not continuous. Okay? Yeah. I'll be okay. I teach math, not spelling. Okay? So there you go. A jump. A jump is something like this, from these 2 points, here to here. If I go bada bada boom, and then it jumps up, bada bada boom. It doesn't even have to be a hole like that. Obviously, it's not continuous here because the graph jumped up. Okay? Infinite. which is really, an infinite discontinuity really talks about an asymptote. So if I go this way from this point to this point, and I go and right here it goes up forever, then it comes from down forever. This goes up forever to positive infinity. This goes to negative infinity. Okay, there's an asymptote here. I obviously couldn't draw that without picking up my pen or pencil. We call that an infinite discontinuity. Or you can just say it's not continuous because there's an asymptote there. All right? A vertical asymptote. Okay, that brings us back to average rate of change. In fact, if I went back to one of the first slides, boop, when we talked about average speed, okay, it was really a change in y and change in x, right? Speed is a change in distance over time, miles per hour, right? That's traffic, that's car, it's distance over time, okay? So if we go back to our current slide, we're really using that same thing, but we're applying it to rate of change of a function of a graph, not so much of an object moving. It is still change in y over change in x. If they want the average rate of change, you are going to be given 2 points. Okay, it might be an x and a y. We call that x2, y2, x1, y1, and we do a change in y over change in x. That ends up being y2 minus y1 over x2 minus x1. It's the same thing as the average speed, okay, or the average change in speed, all right? But, mister, what happens if this is a t in the bottom? Good, then call it t2 minus t1. It doesn't matter. On a graph, I think you can locate the x-axis. You are still good. The average rate of change is 2 points, okay? The instantaneous rate of change, okay, on a graph, if I have something that looks like this, okay, we just did average. Average would give you 2 points. It would give you the point here, and it would give you some point here. And if I find the average, it's just boom. It's those two, correct? Correct. All right? In fact, I'm going to do something here. I'm going to do this. And then I'm going to do another one right here. Okay? So average is that dashed line, wherever the slope of that line is average. The instantaneous rate of change is the change at 1 point. Okay? So if I do this at this point, let's say right here. Ooh, let's do that in yellow. Purple for a reason. Okay, right there, that point. Well, what I'm going to be doing is I'm going to take the average there. I'm going to move these 2 points closer and closer together. Okay? So it's going to get to the point where, okay, these 2 points are going to be so close, they're going to be right on top of each other that it looks like it's 1 point. Okay, the distance between your 2 points are so close. That's what this represents. The distance between your 2 points, it's nothing. Okay, the distance between your 2 points becomes nothing. So you're really finding the slope at this 1 point here. It's a tangent line. It will look something like that. Something like that. Okay? And you use our definition of a derivative, which we will talk about in Unit 3 review. It's this thing here, f of x plus h minus f of x all over h. I am not given 2 points, okay? I have at 1 point. Okay, so I've got to do some algebra to manipulate that. All right? So how would this look? All right, well, let's do an example here. Let's say they give us a function, f of x equals x squared minus 6. Okay? And they want us to find the instantaneous rate of change when x equals 4. Okay? I need to take this limit here and apply it to my function. Okay? So, first off, I need to take x plus h and put it into my function. Okay? So wherever there's an x, I'm going to put x plus h. Okay? Wherever there is an x, I'm going to put x plus h. So it's x plus h squared, because that's where my x is. I still have my minus 6. Can't forget that, minus 6. Okay, minus the original function, which is x squared minus 6. X squared minus 6. I put that in parentheses because I got to subtract the whole function. All over h, and that's the limit as h approaches 0. All right? Now you're saying, well, should I put my 4 in for my x's now? I always wait till the end to put my x in. Okay? So let me explain this now. I've got to FOIL this. X plus h times x plus h gives you the following. X squared plus 2xh plus h squared. If you didn't know how I got that, I took x plus h and multiplied it times x plus h, and I FOILed it. Okay? And that's what I get. I still have my minus 6. And then I've got to distribute this minus sign to all those terms. So minus x squared plus 6 all over h. This is still the limit as h goes to 0. Okay? Now, if I did this right, two things should always happen. They should always happen. The first thing is everything on top that does not have an h should cancel out in my numerator. Or everything from these two terms should cancel out, which are now these two terms, right? So I have a negative x squared and a positive x squared. Okay, they cancel. I have a positive 6 and a negative 6. They cancel. Okay, my original function, whatever it turns out to be, should always cancel out, and it does. That's the first thing that should always, always happen. If that doesn't happen, you've done something wrong algebraically. Okay. The second thing that should happen is everything now has an h. Why is it important? Because I can't plug a 0 into h. Can't. Bottom can't be 0. Denominator cannot be 0. Oh, it's still here. Can't do it. But now look. If everything has an h, I can cancel one h out of everything. Boom, gone. Instead of h to the 2, that's h to the power of 1. There was an h to the 1 here. Boom, that's also gone. What do I have left? 2x plus h. That's it. 2x plus h. At x equals 4. Because remember, x equals 4. And this is the limits as h goes to 0. Now I can do this. My 0 goes in for h. And for my x, goes to 4. 8 plus 0, it's 8. That is going to be the slope right at the point. Remember, we did not have 2 points to do change in y over change in x. We couldn't do this. We only had 1 point. We didn't have 2 coordinates. We had 1. Okay? So I come here, and at that 1 point where x is 4 on my graph, the tangent line, the slope of the tangent line would be 8. It's really a beautiful thing. Okay? Equation of a line. You will be asked. You will be asked to come up with an equation of a tangent line, equation of a normal line, the equation of something sort of line. Okay? We are all really, really comfortable with slope-intercept form. Y equals mx plus b. Okay, we're comfortable with that. Done it for years. Okay, and you can use that. But in calculus, this one is so much more useful. We don't really ever use this one anymore. We can manipulate point slope. Okay, this next one I'm about to show you into slope-intercept. Okay, quick review. Why do they call it slope-intercept? Because this is your y-intercept, and this is your slope. Okay, this is called point slope. How come? Because you're given a point and a slope, not the y-intercept and slope. So it is y minus y1 equals your slope times x minus x1. Okay, the point, okay, and let me do this. Every equation always has a y and an x in it. So you need to have a coordinate that they give you, and they go in for this x1 and y1. They don't go in for just the x and y. Let me repeat that. The x value and y value that you get, or that you come up with from the equation, have to go into x1 and y1. And then I have my slope. How do I get my slope? using this equation right here. Using this limit, it will give you the slope. All right? So we will use that here moving forward. Now, but I like y equals, mister. Good. Then if you want, add y1 to both sides. And there you go. Now it's y equals. Okay, and you can distribute your m and do whatever. But when you are first writing this down to come up with the equation, you write it like this. Okay? Now, what's a normal line? They'll tell you to come up with the equation of a tangent line. Okay, let's say this will give you the equation of the tangent line. I don't know if you remember a normal line from geometry. The slope of my tangent line, okay, I can come up with the slope of my normal line, okay? So the slope of my normal line is the negative reciprocal of the slope of my tangent line, okay? So if I were to come up with a normal line, everything would be the same, okay? If this was my tangent line right here, okay, the slope of the normal line, the only thing that would switch would be my slope, okay? I would have to take it, I would negate that slope of my tangent line, and then make it the reciprocal of that, okay? So let's say I have a tangent line that's y minus 2 equals negative 3 times x plus 4, okay? The equation of my normal line, everything's the same. Y minus 2 equals, I still got x plus 4. The only thing is, if the slope of my tangent here is negative 3, the slope of my normal line, I negate that, it becomes positive 3, and I flip it. Reciprocal, 1/3. That's the only thing that changes. The slope is the only thing that changes. Okay? That's another reason this way is a million times better than slope intercept. Okay? There you go. Simple. All right. Let's do some application. I love these types of problems because you will be asked to do this. Find the equation of the tangent line. The minute they tell me that, I know I've got to use y minus y1 equals slope times x minus x1 of 4 minus x squared at the point where x is 1. Great. I already have my x value here, x minus 1. Okay? How do I get my y value? F of 1 equals, okay, this is your x, this is your y. I just plug a 1 into my equation. 4 minus 1 squared is 3. So my y value is 3 there. Okay, that was simple. Got this. The only thing I need is my slope. My slope, okay, is the limit as h goes to 0 of f of x plus h minus f of x all over h of my function. Okay, of my function. So I'm going to take x plus h and throw it into this x here. So it is 4 minus x plus h squared minus the original function, which is 4 minus x squared all over h. All right? Now, I know that if I FOIL this, I get x squared plus 2xh plus h squared. But I still need to distribute my negative to all of these. Okay? And when I do that, I got 4 minus x squared minus 2xh minus h squared. That is this. I distribute the negative sign here. Minus 4 plus x squared all over h. And if I did this right, two things should happen. Okay? Everything without an h should cancel. Negative 4, positive 4. Minus x squared plus x squared. Done. And what does that mean? Everything has an h. So now, remember, I'm trying to get h to be 0. I can't here. 0 in the denominator. Can't here. 0 in the denominator. Oh, nice. This h cancels with one of these. and cancels with this one. Negative 2x minus h is what I have left. So my slope is the limit as h goes to 0 of negative 2x minus h at x equals what? 1. Okay, so my x is 1, so it's negative 2 times 1. And my h is 0, right? Minus 0. So it's negative 2 minus 0. Negative 2 is my slope. This is the equation of the tangent line right there. The biggest and most heavy work you do, which is just algebra, foiling, combining like terms, and canceling, is when we use the limit as h approaches 0. Okay? This is not bad. And last but not least, meh, these are hardly ever used, so I would just refer to them on your note sheet. I'll just refer to them on your note sheet, and when they come up, use them. These are just definitions. They're just trig limits to memorize. They don't come up all that often. Meh, use them. All right, there are some problems at the end of this packet, and when you're done, if you go to my teacher site, which is in the description, below, there are more packets to practice even more limits and continuity. All right, you have any questions, leave some notes, hit me up, call me. I'll see ya.